Okay, so today we are going to discuss graphing rational functions. We're going to start with this. Everything's posted on Schoology. So to start with, you should read the directions and pause the video and try to work through the graphs and the rest of the problems on the first handout, Introduction to Rational Functions. So you're going to use your calculator. You want to maybe play around with the window, but some just basics. Zoom 6 is normally a good window. You want to make sure your plot's off. And you're trying to determine the asymptotes or the domain and range so you can get a good working sketch. The table function of your calculator would be a great place to find some points to plot and help you with the asymptotes. And once you have the asymptotes and a couple of critical points to get the curves fairly accurate, then you can identify the domain and range. So some other things, if you look in the table, if you look near the X value of where you think the vertical asymptotes are, that should give you both a confirmation of the vertical asymptotes and also some good points to plot. So for example, I put the second function in the calculator. Notice I don't have any plots highlighted. And from there, if you use Zoom 6, it'll give you a window that looks like this. So that's just Zoom 6. So based on this graph, it looks like there's a vertical asymptote separation somewhere in here, and there's a horizontal asymptote somewhere in here. But if I go to the table, right here at x equals -4, I get an error. So that confirms that the vertical asymptote is in fact at x equals -4. And I can see right on the other side of that some nice, neat points to plot. They won't always be nice and neat, but around your vertical asymptotes is a good place to look for points to plot. If you can't really tell exactly where the horizontal asymptote is, you can try and take a good guess and go to y equals. And so let's say I think it's y equals 1. Well, that can't be it because it crosses over this part of the curve. So I'm going to go back and adjust that up a little bit. And y equals 2 seems to fit nicely between the two curves. You can always expand your window if you want more confirmation, but this is just an introduction. So pause your video and try all of the 6 graphs. Try and get the best graph you can by using your calculator, and then start the video again and we'll go through all the answers. So the first two problems, there is a vertical asymptote in number 1 at x equals -5 and a horizontal asymptote at y equals 0. I got a couple points on either side of the vertical asymptote from my calculator, and that also will help me with my domain and range. The domain should be tied into any vertical asymptotes and the range tied into any horizontal asymptotes in most cases. And remember that your graph should go through the points that you plot and hug any asymptotes that you have. Notice in the domain and range, I've used parentheses because of the asymptotes. So then in number 2, that's the one that I graphed on the calculator. It looks like we have a vertical asymptote at x equals -4, a horizontal asymptote at y equals 2. I got a couple of points off the table from the calculator to plot, drew my curves through those points, hugging the asymptotes, and that led to my domain and range. Then in number 3, getting a little bit more complicated, you can factor the denominator. And so this time we have 2 vertical asymptotes. The vertical asymptotes are going to kind of drive your curvature. There should be some curve around every vertical asymptote. So if you have 2 vertical asymptotes, then there'll be something to the left, in between, and to the right. And so you can see my domain got a little more complicated because of the two vertical asymptotes. I have negative infinity to the first vertical asymptote, then negative 3 to 3 between the two vertical asymptotes, and then 3 to infinity to the right of the other vertical asymptote. And then the range was negative infinity up to the horizontal asymptote, which is at y equals -2. And then because the curve that was between the vertical asymptotes had a lowest y value of 0, or it was right above 0, I don't actually think it was on the origin, then we use the parentheses, but 0 to infinity. So it doesn't just go -2 to infinity, because there was actually no points between -2 and 0. For number 4, again, we can factor the denominator, which ties into your two vertical asymptotes. And then we had a different curve that happened between the vertical asymptotes this time. It wasn't parabolic, it was more cubic, like a negative cubic function. So I just put a bunch of points down off of my table so I could be more sure of the way the curve was going to go. Again, the domain is tied to the vertical asymptotes, and in this case, because of this middle curve, the range is negative infinity to infinity. Then on the other side, okay, for number 5, you can factor both the numerator and the denominator, and then you can reduce the factor of x minus 1. Remember from limits that creates a hole at x equals -1. And so once I reduce that, the function I'm working with is just x plus 1 over x plus 7. And if I take this x value where the hole is and I plug it back in for these two x's, I'll get 2 over 8, which tells me that the y value of the hole is 1/4. Okay, so I have my one vertical asymptote tied to the remaining denominator. I have my horizontal asymptote at y equals 1, and then I got some points from the table, drew my hole at that point 1, 1/4. And then so your domain is negative infinity to the vertical asymptote, and then the vertical asymptote to the x coordinate of the hole, and then the x coordinate of the hole to infinity. So the hole is in place of a second vertical asymptote, so it is involved in your domain, and it'll also be involved in your range. Negative infinity to the y coordinate of the asymptote, and then the y coordinate of the hole, and then the y coordinate of the hole to the asymptote, and then the asymptote to infinity. Then in the last one, instead of a horizontal asymptote, we had a slant asymptote. And it might be hard just looking at your calculator to figure out exactly where that was. But if you use the long division that we talked about previously, you get the equation y equals x minus 5, which actually will tell you where that slant or oblique asymptote is that takes the place of the horizontal asymptote. We still have a vertical asymptote tied into this denominator at x equals -1. So you have to adjust your window a little bit on here because this part of the curve will be off your graph if you don't adjust the y-min. The highest point on this curve at the bottom of your graph is at 4, -12. And then you've got lots of points you can plot to get this curve. So your vertical asymptote is at -1, that's tied into your domain. Your range is a little different here because of this slant or oblique asymptote. It goes negative infinity to the y coordinate of the highest point on this curve, and it's a bracket because that point does exist. And then the lowest y value of this part of the curve to infinity, and again a bracket because that lowest point does exist. So got some questions. In general, what connection can you make between the vertical asymptotes and the equation? For the vertical asymptotes, if you set the factors of the denominator equal to 0 and solve, you will get your vertical asymptotes. If you look at number 5, though, we were able to factor, but we were also able to simplify. So you want to set those factors in the denominator that are left after simplifying to get your vertical asymptotes, because if you can simplify, then you will have a hole instead of a vertical asymptote. You may or may not have made the connection for the horizontal asymptotes, but it actually just uses the limit as x approaches infinity rules. And you'll find if you go back through those 6 functions and apply those rules when the degree of the numerator and denominator are less than, equal to, or greater than, then it should give you some indication of the horizontal asymptote, or in the case of the last one, you get an oblique or slant asymptote. And let's see, just more review of the long division that you'll need in some cases. So for number 7 and 8, remember that you are just looking at the what you're dividing by and what you're dividing into, those first terms. So x times 2x is what would give you 2x squared. So that's why that's a 2x up here. And then you multiply 2x times the whole binomial here, and that's where you get 2x squared minus 10x. But then you're subtracting, always subtracting. So 2x squared minus 2x squared, that will always go away. And if that doesn't go away, you didn't use the right thing up here. And then negative 4x minus negative 10x is really negative 4x plus 10x, so you get 6x. Then you bring down the next term and repeat the process until there's nothing else to bring down and you're left with a remainder. So if this was a function that we were trying to graph and we needed to get the slant or oblique asymptote, we would have one at y equals 2x plus 6. So for number 8, you end up with 3x squared minus 8x plus 6. While we won't be working with any parabolic asymptotes, this function, if we had to use it for graphing, we would have, instead of a linear slanted asymptote, it would be a parabolic asymptote. We're just not going to be doing those. And then for number 9, when you do your long division, you get y equals negative 2x plus 4. And in number 10, we get y equals x plus 4. Each time we got a remainder, but we're not going to use those remainders for those slant or oblique asymptotes. Okay, so the new stuff, we're going to graph these rational functions using 6 steps. The first step is we're going to check for symmetry. It's really important that you get this part. Do not do any kind of simplifying before testing for symmetry. If you do simplify before you test for symmetry, then you're not going to get an accurate result. So this goes back to Magnus algebra, and we did inverses with trig. We talked about it. Basically, an even function has y-axis symmetry. This picture over here depicts y-axis symmetry. It's an even function. It has symmetry over the y-axis. And you can tell that algebraically, because if you have an x value and you plug it into your function and you get the corresponding y value, and then you take the exact opposite of that same x value and you plug it into the function, you get the same y value that you got before. So opposite x's give you the same y's. Okay. If it's an odd function, that is origin symmetry. Think cubic functions have origin symmetry. And you plug in opposite x's to the function, but it gives you opposite y's. Okay, so when you check for symmetry, your answer shouldn't be even or odd. It should be that you have y-axis symmetry or origin symmetry. That's the type of symmetry. So the easiest way to test symmetry is just to do a small table of values. These are not going to be rational functions. We're just using them as quick examples. So let's take this parabolic function. So let's do a quick table. You're just going to pick a pair of opposite x's. You do not want to pick x's that are related to vertical asymptotes or holes. Okay, so you got to kind of think about your denominator of your function a little bit before you pick the x's. Here it doesn't matter. So I'm just going to pick -1 and +1, opposite x's. If I plug -1 over here into this function, -1 squared is 1, 1 minus 3 is -2. And then if I plug the +1, I get the same result. So opposite x's gave me the same y's, and that produces a function that has y-axis symmetry. What's nice about this too is that when you're trying to do your final graph, these are points that you could actually plot on your graph too. So the information is not wasted. Okay, so opposite x equals the same y. That's what you're looking for. Origin symmetry. So let's use y equals 2x cubed minus x. Okay, again, you want to pick a pair of opposite x's. This isn't a rational function, but you want to pay attention, not choose x's that relate to holes or vertical asymptotes. So again, I'm just going to use -1 and 1. If I plug -1 in for both of these x's, I'm going to get -2 minus -1, which is -1. And if I plug a +1 in, I'm going to get 2 minus 1, which is +1. So these opposite x's gave me opposite y's. And that would let me know that this is an odd function and has origin symmetry. After you complete the first step, now's the time that you want to simplify. This is where you're going to find out if you have any holes or not. Okay, and if you can simplify, you're going to use the reduced simplified function for everything else. So you do not want to use a simplified or reduced function for the symmetry step, but afterwards, that's when you want to do any factoring and simplifying. And if there is something that you can cross out that produces a hole, then all other steps are going to be completed with that reduced function. Okay, so now is when we're going to simplify. Okay, so vertical asymptotes are related to the denominator, and it's basically the factors of the denominator. So if you set the denominator equal to 0, you may find it easier to just go ahead and factor the denominator. So like the denominator here is the difference of squares. It factors into x plus 2, x minus 2. So that would give me vertical asymptotes of x equals -2 and x equals 2. You can also just set the denominator equal to 0 and solve, but in this case, you do need to remember that when you take the square root of both sides, you have to use plus or minus to get both of those vertical asymptotes. So that first example has two vertical asymptotes, one at x equals -2 and one at x equals 2. Asymptotes are lines, so you want to make sure you state them as equations. So you wouldn't want to just say your vertical asymptotes are plus or minus 2. It's got to be x equals. All right, so for the next example, there's nothing to factor. So your vertical asymptote, you would just set your denominator equal to 0, and you would get that there is a vertical asymptote at x equals 1. Put a little hook on the end of that. The next one, you cannot factor x squared plus 1. There is no sum of squares. So when we set the denominator equal to 0, and we isolate the square term, and you need to take the square root of both sides, get x equals plus or minus. The square root of -1 is the imaginary unit I. So that just means there are no vertical asymptotes here. All right, next one. So if we factor, this time we can factor both the numerator and the denominator. So the numerator is difference of squares. The denominator, two numbers that multiply to give you -21 and add to give you +4. And you can see here that we can simplify. So this would produce a hole at x equals 3, not an asymptote. If we want to specifically know where that hole is, not just at x equals 3, but what is the corresponding y value, we would take that 3 and plug it in for both of the remaining x's, and we would get 9/10. So the hole is specifically at the order pair 3, did I say 9? 6/3 plus 3 is 6/10, and 6/10 reduces to 3/5. So that's where I would actually draw the hole. And everything else I would do, all other steps with the function would just be based on x plus 3 over x plus 7. And I would just set x plus 7 equal to 0 to get the one vertical asymptote at x equals -7. All vertical asymptotes and holes should be drawn in your graph. So you can either wait till you get all your information and start, putting things on your graph, or you can go through all your 6 steps and then do it. The third step is horizontal asymptotes, which also would be instead of horizontal, could be your slant or oblique asymptotes as well. Okay, so we said from the first page that it was going to be related to our limit to infinity rules. So you will always have a horizontal asymptote at y equals 0 if it is a rule 1. Okay, rule 1, remember, was the degree of the numerator is less than the degree of the denominator. The degree of the numerator is 1, the degree of the denominator is 2, that's why it's rule 1. And so our limit to infinity would be 0, and that leads us to a horizontal asymptote at y equals 0. All right, if it is a rule 2, which means that the degree of the numerator is the same as the degree of the denominator, so our limit to infinity, we would look at these two terms and reduce it to 2, and that will be our horizontal asymptote here, y equals 2. And then if it's a rule number 3, the limit would either be infinity or negative infinity, but that's not going to be our slant or oblique asymptote. Obviously, it's going to tell us that if it is a rule 3, which means that the degree of the numerator is greater than the degree of the denominator, then it means the limit to infinity would be infinity or negative infinity, but that tells us that we are going to need to use long division to find the slant or oblique asymptote. I prefer slant, but same as oblique. So we do long division. 3x to the 4th. We have a whole here. It goes x to the 4th x squared, so we want to do plus 0x cubed minus x squared. And we're going to divide by x cubed minus x squared plus 1. Okay, so we would multiply x cubed times 3x to get 3x to the 4th. Okay, so we know this is a 3x. We're going to distribute this 3x to all 3 of these terms. So 3x times x cubed is 3x to the 4th. 3x times negative x squared is negative 3x cubed. And 3x times 1 is positive 3x. When we subtract, if you did the work right so far, then this should always happen. We have 0x cubed, that placeholder, minus negative 3x cubed, which is positive 3x cubed. We have an x squared, and then we don't have an x squared down here. So that would just be minus x squared. And then we have this 3x, so that's minus 3x. And then we keep going. So we would need to multiply x cubed times 3 to get 3x cubed. So that would be positive 3. And we start the multiplication process again. 3 times x cubed is 3x cubed. 3 times negative x squared is negative 3x squared. 3 times 1 is plus 3. Subtract, that goes away. We can really stop here because we don't have anything else to bring down. So we're done with the long division, and our slant asymptote would be y equals 3x plus 3. So once you're done with things to bring down, then you're done with your long division and you have your slant or oblique asymptote. Step 4, we want to know if our graph crosses the horizontal or slant asymptote. We never cross vertical asymptotes, but it is okay to cross a horizontal or oblique asymptote. What happens is there's different parts to the graph, there's different curves, and some part or curve of the graph will cross and others won't. So it's like the horizontal or slant asymptote only applies to part of the curves, but not all of them, and that's where you can have the crossing happen. But we never ever cross a vertical asymptote. So basically, we want to set our function equal to the equation of the asymptote and solve. If you don't get a solution, then your graph does not cross that horizontal or slant asymptote. If you do get a solution, that is where the crossing happens. So for this one, if we start, we got to figure out what our horizontal asymptote is. And this would be a rule 2 We look right there, and our horizontal asymptote is at y equals 3. So we would set our function, the whole thing, equal to the horizontal asymptote. And then we're going to solve that equation. So we would multiply both sides by the denominator. So we have our numerator equal to 3 times this denominator, just distribute. And then we're going to solve that equation. We have 3x squared on both sides, so luckily that'll go away. And let's see, if you subtract this 3x, you'll get negative 6x equals negative 12, and then x equals 2. So this one does cross. F of x crosses your horizontal asymptote at x equals 2. Okay, step 5 and step 6, x-intercept and y-intercept, last pieces to our puzzle. The x-intercept for pretty much any function is always going to be a little more challenging than the y-intercept. So you get to end with like the easiest part. So for the x-intercept, you always just set the numerator equal to 0 and solve. The x-intercept is where y equals 0. And if you think about it, if I make this whole side of the equation equal to 0, my next step would be to multiply by the denominator, but 0 times the denominator is still just 0. So that's why we're going to set the numerator equal to 0. So we've got 3x minus 4 equal to 0. So 3x equals 4, and x equals 4/3. So we have an x-intercept of 4/3, 0. That's a point that we can plot on our graph. Here, if we set the numerator equal to 0, you could factor and set the factors equal to 0, or you could do it this way. When you take the square root of both sides, though, don't forget the plus or minus. So we have 2 x-intercepts here. We have negative 2, 0, and 2, 0, so 2 x-intercepts. If you set the numerator equal to 0, like this example right here, if I set the numerator equal to 0, that doesn't make any sense. What that tells you is this has no x-intercept, probably because your horizontal asymptote is the x-axis. And then on number 6, the y-intercept is where x equals 0. And so here, for this first example, if you put zeros in for all your x's, you're just left with all the terms that don't have x. So you'd be left with negative 4 over 1, which is negative 4. So your y-intercept here is 0, negative 4. Here you'd be left with 2 over negative 3. So your y-intercept is 0, negative 2/3. And here you will be left with 2 over 0. That means there's no y-intercept. So for every problem, you want to go through all 6 steps showing your work and then use all pieces of information to get a graph. You may still need some extra points to get a clear graph, but this should get you a long way. So we're going to end up with just a couple of examples. So the first one, so remember we're going to start with symmetry. So step 1 is symmetry. And so if I look at this, I can just see that the denominator will factor. I don't want to cross anything out yet. Remember, we're not simplifying here. But when I do my symmetry table, I don't want to pick x values related to any vertical asymptotes or holes. And so I can't use 1 and negative 1 for this one. So for that reason, I'll just do the next best thing and do negative 2 and 2. So you're going to substitute those values into your function. And when you plug in negative 2, you get 2/3. When you plug in positive 2, you also get 2/3. That means that we have y-axis symmetry. So when we're done graphing, we should be able to see that show up in our graph. The next step is our vertical asymptotes. So I already factored my denominator, so I can see that I have x equals negative 1 and x equals 1, so 2 vertical asymptotes. Next step is horizontal or slant asymptotes. This is a limit it to infinity rule 2. Okay, the degree of the numerator is the same as the degree of the denominator. So that would tell me that it would just reduce x squared over x squared, and y equals 1 would be my horizontal asymptote. Number 4, does the horizontal asymptote get crossed? So we set the function equal to the horizontal asymptote and solve, multiply both sides by the denominator. The x squareds will cancel out, and you're left with -2 equals -1. Well, that doesn't make any sense. So that means that the horizontal asymptote is not crossed. Number 5 is your x-intercept. X-intercept is what you get when you set your numerator equal to 0. So we have 2 at plus or minus the square root of 2. And last, we have y-intercept. Y-intercept is what you get when you replace all the x's with 0. So if you do that, you're going to have -2 over -1 or 2. So we have 1 y-intercept. All right, so when we go to the graph, let's see, we have 2 vertical asymptotes at x equals -1 and x equals +1. We have a horizontal asymptote at y equals 1. We don't cross that horizontal asymptote. We have 2 x-intercepts. Square root of 2 is about 1.4. So -1.4 and +1.4. And we have a y-intercept at 0, 2. And then we can also plot these points if we want to use those as well. -2 and 2/3 and +2 and 2/3. So we're going to go through all points and cross no asymptotes. Through the points, hug the asymptotes. That's why we have to do the step 4 to see if that horizontal asymptote gets crossed. Remember, vertical asymptotes never do. And that would affect the centerpiece. If the horizontal asymptote did get crossed here, it would happen here in the center. All right, one more example. So again, you can think about factoring the numerator if you want, but when you do the symmetry, you don't want to cross anything out anyway. So when we do our symmetry table, we can see that our vertical asymptote is going to be at x equals 2. So we can't use 2 or -2, so we'll just go back to our -1 and 1. If you plug -1 into the function, you get 12 over -3, which is -4. And if you plug 1 in, you get 2 over -1, which is -2. So our opposite x's did not give us the same or opposite y's, so there's no symmetry here. That's going to happen more often than not. It's pretty rare to get symmetry. We could see from the first example, we did in fact get the y-axis symmetry from an even function, but more often you're going to get no symmetry. Your vertical asymptotes, there was nothing to factor in the denominator, and if you set x minus 2 equal to 0, you just get x equals 2. The horizontal asymptotes. All right, so this would be a limit to infinity rule 3. The degree of the numerator is 2, the denominator is 1, and so that's going to be a slant or oblique asymptote. That means long divide. Okay, so we would multiply x by 2x to get 2x squared. Okay, 2x times x is what would give us 2x squared. So multiply 2x times -2 is -4x. Subtract. -5x minus -4x is -1x. Bring down the 5. X times -1 is what would give us -x. And then -1 times x, -1 times -2. And 5 minus 2 is 3, but that's just our remaining. So our slant asymptote is at y equals 2x minus 1. All right, step 4, we want to see if that slant asymptote gets crossed. So we set our function equal to the slant asymptote and solve. So here we would multiply both sides by the denominator. So we need that FOIL 2x minus 1 times x minus 2. So if you FOIL 2x minus 1 times x minus 2, then you are going to get 2x squared minus x minus 4x is negative 5x, and negative 2 times negative 1 is positive 2. So you can see that the 2x squareds cross out and the negative 5x, and you get 5 equals 2, which makes no sense. So again, we have no cross. All right, let's go back to our last 2 steps, x-intercepts. So if you set your numerator equal to 0, here's where you'd want to think about if you can factor. If you plug that into your calculator, then you'll see that it doesn't, this quadratic does not cross the x-axis, which means that it doesn't have any real roots. If you try and factor it, you would need 2 numbers that multiply to give you positive 10 and add to give you negative 5. That doesn't exist. So without a calculator, that's how you can tell. So there are no real zeros, so no x-intercepts. Doesn't cross the x-axis. And number 6 is the final is y-intercepts. So if you plug 0 in for all the x's, you're left with 5 over negative 2, so negative 5 halves. Okay, so we're ready to graph. We have a vertical asymptote at x equals 2. We have a slant asymptote at the line y equals 2x minus 1. So we got to kind of graph that line. Negative 1 is the y-intercept. Slope is positive 2. We're not crossing in either of our asymptotes. There's no x-intercepts. There is a y-intercept at 0 and negative 2.5. And we kind of need some more points. But if we go back up here to our symmetry table, we can use the point negative 1, negative 4, and we can use the point 1, negative 2. So we've got like 3 points to get this part of the curve. And then you can just use your calculator to find a point to plot up here. I'm pretty sure it goes off your graph, but it should be some sort of parabolic general shape and hug your asymptotes. Use your calculator just to find a point so you have some sort of accuracy. Okay, so that's it for the lesson. Your assignment for this week is posted. It is called To Infinity. So you have, using the 6 steps, collect enough information about the behavior of the following functions to graph them, sketch the graph on a separate sheet of graph paper, unless you feel like you can fit everything in there. So this is the assignment that is due for this first week of the emergency learning plan. A single PDF, please. And that is due by Friday at 11:59 p.m. Please let me know if you have any questions during this week's office hours, or you can email me or send me a Schoology message. Thanks.